This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Working? Good. All right. That's testing. Working? Yeah. Okay, so today we're going to look at input and output from the embedded system perspective. It might seem somewhat trivial, some of the input and output protocols and things that we're going to talk about, but towards the end of the lecture you may get an appreciation of how difficult it is, particularly when we're talking about real-time embedded systems where there are tight timing constraints or crucial timing issues that need to be managed or at least predicted. So what I want to do is I want to highlight to you the problem with embedded systems and how we try and bridge the gap. Okay, and this is going to form the story for the next sort of 3, 4, 5 lectures when we start talking about timed automata and continuous time systems, discrete time systems, state machines, etc. So I'll just motivate things by drawing 2 domains. The cyber domain and the physical domain. And embedded systems bridge the gap, right, between the two. So you could say the embedded system bridge gap between the two, right, cyber physical systems. So what are the properties of the cyber side? Well, just think about programming, right? When you are writing something in C or doing something for, say, an Arduino board or something like that, everything's digital. Okay, it's no concept of analog when you're programming something in C. Things happen in discrete time. So you are talking sample rates and things like that, right? N as in, you know, the sample number that you're up to. And everything is done sequentially. In that we're issuing instructions in a certain order, you can trace your C code, you know an instruction follows another, etc. It's all fairly predictable. Now on the physical side, I think you can probably guess what's going to happen, right? We're going to flip everything around. That we don't live in, I guess we can call it a continuum. We don't live in a discrete digital environment. Okay, so we live in analog. That's the obvious opposite of digital, but I'll call it continuum. Right, we live in a continuum, and that also almost covers that everything happens to us in continuous time. Okay, we're not chopped up into samples or anything like that. But one of the biggest issues is that the real world is concurrent. And that's going to highlight what we're going to do, particularly today when we look at interrupts, but also when we start looking at state machines, particularly hybrid state machines. Okay, so Physical world's concurrent, two things can happen at once independently, whereas in the cyber world, everything is really pretty much sequential, right? There's a fixed order to things running. And this is, as I said, one of the most difficult things, reconciling the two here, going from a concurrent, continuous time, maybe a dynamical system here, into something that's chopped, sequential operations and in discrete time. Okay, so how do we get from the two, one to the other? We are going to look at this in terms of an input-output perspective. And when you want to design an embedded system, these are the sorts of things you have to consider. Are your inputs going to be analog or digital, wired, wireless? Right, wireless might sound convenient, but it adds a hell of a lot of complexity and also issues to the system. Serial versus parallel, that's not an obvious decision as well, to do with space and time and things like that. Bit rates, sampled, event-triggered, physical connectors, electrical requirements. The list goes on. When you are designing embedded systems products, it's actually much more complicated than you think, particularly when you have to start thinking about even things like physical connectors. Yeah, and if you ever go to an online retailer or wholesaler of electrical parts and try and look at electrical connectors, there's thousands. Okay, so even just choosing one is not simple. Okay, so let's look at a typical system. And the system here, a little development system, is a BeagleBone Black. Has people used a BeagleBone Black before in signal processing or anything like that? One person? Yeah? No? No one. Okay, what's so good about it? It's just an example of a little embedded platform. It's nice because it has a bunch of peripherals and also these dual inline headers, well, these multi-pin headers here, where you can clip on. Arduino calls them shields. BeagleBone calls them capes, I think. Same thing, right? You can plonk stuff on top of here and interface via the pins and talk to all the particular things on there. So it has analog, digital inputs. It's also nice. It's made by Texas Instruments, so it means it's closed source. Okay, so they've got a whole bunch of drivers and things like that that are proprietary, and that's good in one way, and it's bad in another. So it's good in one way in that you've got some big monstrous company that's kind of knowing what they're doing, hopefully, and they've locked down the hardware so that there's no hackers coding up stuff and distributing it on the net as such. But it's bad in that there's not that sort of community where it can get down into the nitty-gritty and start mucking around with things, like there is with Arduino, right? There's a massive community of people developing on that. Okay, so just an example of the sort of I/O configurations that this has. There are two, as I said, those two ports there, if you like, headers, and it's called P9, that one, and P8, this one. It offers an absolute plethora of input-output possibilities. So P8, for instance, can be configured as this general-purpose I/O, and you can see the numbers start getting pretty high in terms of how it indexes them. And the other one, P9 here, has things like SPI, has general purpose input outputs as well, but particular input output formats, basically. SPI is an example of something called serial peripheral interconnect. And the interesting thing about this board, if you ever decide to play around with it, is there's actually 8 configurations available. There is a register, a 3-bit register, that you write to on the micro here, on the board, I should say, that basically configures 8 possibilities of these setups here. This is one particular configuration here. By I2C, you write to it. Sorry?
One of the 8 configurations.
Sure. You write a 3-bit number to a register, and it basically will switch these to inputs, outputs, or connect them to the various blocks inside here in order to do SPI or whatever. All right. There's also analog ins and or the supply pins and stuff, which generally don't tend to change. Okay, the interesting thing here is that with these general purpose I/O pins, and that's common amongst Arduino, Raspberry Pi, any sort of little embedded platform, that they can be reconfigured also to be PWM drivers timers. Now, these are, interestingly, set under software control. Now, where that can be an issue is that what if the software gets out of control? Typically, we delineate software and hardware, right? The hardware is locked in and the software just runs on it. But embedded systems like this, particularly development boards, allow you to reconfigure it in software. So if you've got a poor software programmer or something goes wrong in the code, you can actually get hardware failures. A classic example would be if you've got some of these GPIO ports set as outputs and you're driving them at 5 volts and somehow it gets reconfigured as an input or something like that and 0 volts gets shorted into it, you can get a supply short on them. Okay, so if you're accidentally switching these things from inputs to outputs, you can have some disastrous results. And that's not as silly as you might think, that, oh, well, if someone goes and writes a piece of code that changes this from an output to an input, that's bad, obviously. But it could happen from a stack overflow, for instance. If the stack starts getting out of control and starts overriding registers, you can actually have these hardware failures. So it's a software problem, not a bug as such, but not an inherent bug. Or it's an inherent bug that can cause hardware failures. Okay, so let's look at these GPIO pins. One way of getting mass I/O into these things is to use what are called open collector circuits. Now, essentially what these do is they allow hardware ORing of multiple devices. Okay, so typically if you've got multiple micros or multiple units tying into the one line here, you've got problems, right? If they're both sharing some sort of common line and one wants to drive a 0 and one wants to drive a 1, you've got a short, right? Hardware failure, smoke, basically. So one of the simplest ways of doing it is using open collector circuits. So these are outputs which can be driven by registers, for instance, that have only one transistor able to drive the pin value. What do I mean by that? If you've ever seen the inside of logic gates, typically there are 2 transistors, like in a push-pull configuration, right? One of the transistors can grab the 5-volt line and put it out, and the bottom transistor can suck current down to the 0, so you can get 5 and 0, or 1 and 0. In this case, you only have the lower transistor, basically. So what it means is a register will, if it puts a 1 on the register, you write a 1 to the output pin, then the transistor turns on and you have a direct current source to ground. Right, so you're essentially seeing a 0 here. It's inversion. So you write a 1 to the register, the pin gets pulled down. Now, the beauty about this is that if any of these other lines are at 1, at the register, it's hard to see on this 3D get in behind here, but if the register itself is 0, then essentially these are disconnected. Okay, if the transistor is off, then those lines are disconnected. And if one of them turns on, that's okay. We can all understand that if we short 0 to 0 and that becomes on, then there's no problem there, right? What this requires is it requires a pull-up resistor, and the pull-up resistor is providing the logic high. So we're not actually trying to drive two things into logic high. So this is called a hardwired OR configuration, or in this case it's actually a hardwired NOR, because you've got to write a 1 to get a 0 on the pin, and if you write a 0 it's pulled up via the external pull-up resistor. Okay, we have to put a resistor there typically because when those transistors are on, they're pulling current through the pin of the device. Okay, so you've got a nice big chunk of current coming down through here being sunk through the device, and we don't want too much current going through microcontrollers. They can't handle much, so typically we limit the amount of current via a pull-up resistor. Okay, so that's called a hardwired NORing. And typically if you do Arduino or you do Raspberry Pis or something like that, you can use open collector outputs to do that sort of thing. So that's basic GPIO stuff, general purpose input output. What about more complex arrangements? And they broadly fall into two categories. Parallel, think of this as one wire per bit. So it's like it's a space thing, it's in space. And serial, which is one wire per direction. So think of that as in time, right? It's over time. So parallel is space and serial is time. And here are some examples of the different standards and things out there. What can we say about these? Well, I'm pretty sure you've never heard of ATA. PCI, I doubt you've ever used a computer with PCI. You probably use many computers with PCIe, but these things were around when I was, hacking around with this sort of stuff as a young guy. But these days, none of this stuff really exists anymore. Now, the funny thing is, why doesn't that stuff exist? Because parallel is difficult to do at high speeds. In the old days, it used to be, well, if we can just get 8 wires happening at the same time, we can just, get 8 times the data down the other end. And who cares if the connectors are a bit bulky like SCSI here? Who cares? Portability is not a problem. Devices aren't small. They're these big things that sit on a factory floor, right? You don't want to move them. You don't care. People aren't going to be ripping these things out and connecting them. But over time, what happened was processor speeds got faster and clock rates got faster. Noise was understood better, that sort of thing. And it actually becomes better to do things serially. The connectors become smaller. USB only needs 4 odd connectors or something like that. And there's USB. Things are all done now in serial. It's funny that you think that 1 bit at a time is actually quicker than getting 8 bits in parallel. Now, another reason for that would be that with parallel, you have big skew problems. Okay, so it's not easy getting 8 bits down 8 different wires, even if they're enclosed in some sort of wrapping down the other end, and to have them all arrive at the same time. Okay, so skew is a massive problem with parallel stuff, that if things arrive slightly differently and they're latched in at the same time, they're latched in, but sometimes some of the signals haven't arrived, you get big problems. Okay, so yeah, serial is the way to go. But that means that we have to be a bit more clever about bit alignment. Okay, so I'm going to take you through the simplest version of bit alignment called RS-232, and that hints at how things might be better done in, for instance, USB. And USB is quite tricky in how that it actually sends packets, right? There's synchronization frames and stuff like that going on there. Okay, so I'm going to show you an example of a serial communication protocol that's been around for more than 50 years, probably almost 60 years. It just does not die. Now, luckily, it's been killed on laptops, it's been killed on desktops, but there is tons of industrial equipment, legacy equipment out there that uses this protocol. So it's a nice way of showing how you can serially signal stuff down a bunch of wires. Now, RS-232, as I said, it started off 50 or 60 years ago. It started off with something like, 30 connectors or something. It was crazy. And then it eventually got whittled down over the years, and I think it's 9 control wires now. There are 9 control wires to send a single bit stream. It's pretty crazy. So it's an example of what's called an asynchronous serial connection, and most setups these days are asynchronous serial connections in that there's no common clock. So one device is not sending a clock to another one, okay? Difference would be JTAG, for instance. JTAG differs slightly in that there's a clock actually being sent to the other guy. But there's no clock. So how do you get synchronization between the two things? If this thing's sending a bit at a time over some time period, how do you actually know when to be grabbing it? Very simply. So the idea is what you do is you have a shared data and control line, right? You've only got one wire that's essentially passing the information down. So you've got to use it for control and for data. How on earth does that happen? So what happens is there, I've got a toolbar over the top of this, but underneath this, I don't know if I can, I can point under it. Okay, so RS-232, you can see has these, massive voltage swings in -15 to +15. And the formatting is that to send a 0 and to send a 1, you send a 0 by sending a voltage in the range of +3 to 15 volts. Okay, remember, this is a legacy thing from the 50s or 60s. So voltage swings like that weren't uncommon, particularly for electromechanical sort of devices. And you signal a 1 by swinging a negative voltage. Now, the interesting thing about the RS-232 protocol is that, as I said, it's a shared control and data bus line. So what happens is when the system's idle, right, it's holding, you hold a negative voltage, okay? As soon as that voltage starts going positive, that's the control signal to essentially start the transmission, and it's called the start bit. So once that is detected as a 0, up in the positive region here, then the receiver will then start just clocking in bits, right, over an 8-bit period. Okay, so basically, bang, as soon as that goes high, it then waits, it knows something's coming, start your clock, and then these are the bit periods here, right, signalling certain values coming out. So the sender and the receiver have to agree on some sort of agreed clock rate to be clocking in the bits. You know when it starts and you know when it stops. So the protocol is one start bit, for instance, 8 bits of data and a stop bit to then get it back to the idle state to wait for another start bit. It's a bit of overhead. You're sending 8 bits, you need 2 bits of overhead to do that. So for instance, if you wanted to send the ASCII character 4B, which is K, capital K, 4B, you clock it out least significant bit first, up into the most significant bit. And something on the other end will be buffering that into a buffer here which loads the LSB first and ends up with the MSB. And then clocks it out in parallel. So RS-232 is just an example of a UART. It's asynchronous, and it has, all UARTs basically have the same sort of format here. I'm not going to go into too much detail, these are just basic block diagrams, but you have registers here that either take something in parallel, 8 bits, and then clock it out serially, 1 bit at a time, via FIFO, or receive it one bit at a time and stack it up into an 8-bit byte and then basically pass it on to wherever it needs to go. So these registers are called shift registers, okay? They're just concatenated D flip-flops that just pass the information along and shift it as it goes. So there's many different implementations of UARTs. As I said, this is just an example of one here. Right, so why RS-232 works is, so remember it was invented many years ago, back when things weren't super great in terms of clock rates and stuff. How it works is that it works where things are just close enough. Close enough is okay, but it also means it's not very fast. So if the transmitter clock is close enough to the receiver clock, then as long as you sample it 8 times, if you're a few hertz out or even, a few hundred hertz out, by the time you've sampled it 8 times, it's still not too bad, okay? That's all right. But where we start running into problems is where if we need really tight timing, okay? We want to get this stuff blasted out very quickly, clock rates are fast, any sort of skew or non-alignment of the bit periods here can cause big problems. So, for instance, if you're interested, what USB does is it gets a much higher speed by every packet that gets sent. A synchronization sequence of 8 bits is sent out in order to lock the two things together, basically, and the receiver clock locks onto that. So RS-232 is pretty slow. I think it has the fastest possible bit rate is something like about 57,600 bits per second, which is damn slow when you think about how USB works. Okay, so how do you actually get input and output in software? So that's the hardware side of things. There are these registers that stack things up and stuff, but a lot of that should be hidden from the programmer. As a programmer, you would like to just be able to write functions or use other people's functions that can just give you what's on the input, or you magically send something to a function and it churns the hardware to send it out. Actually, I'll just show you, just as an interesting point, I just forgot, that oh, it's not in yet. If you want to see what that RS-232 signal looks like when it's actually received, you have a lot of analog effects going on there, right? So that's the signal there. So you've got the start bit, then 2 1s, a 0, a 1, etc. And that's what it looks like on an oscilloscope after it's been received. So there's the 0 point, there's the massive voltage swings that RS-232 uses, and you can see lots of sort of second order-ish effects here of ringing, right, overshoot and all that sort of stuff as it does the big swings. So it's not as clean as the ideal situation here. Okay, that's just out of interest. All right, so there's 2 ways of getting input and output in software: polling or via interrupts. Now, polling is pretty simple. You've got a loop, and basically you ask each device or pin what its state is. So if the input's ready, you read it. If the output needs to be produced, you produce it. It's very simple, it's very predictable, but it doesn't make use of resources very effectively, particularly in cases where you may have inputs that happen at different times or different frequencies, right? Someone smashing a keyboard might be updating a lot more, right, its state versus, I don't know, a light sensor or something, which an ambient light sensor wouldn't change too much, particularly indoors, right? So polling, yeah, it's predictable, but it's not very useful. Interrupts. Interrupts are fantastic. You basically have some sort of external hardware, and it tells the processor when something's ready. So input's ready, okay? Something's happened, go and read what that data might be. But that means there's a whole bunch of machinery that needs to be added on top of it. In particular, the processor has to suspend what it's doing. You have to invoke an interrupt service routine, and then you have to interact with the application concurrently. So in other words, think of it, you're sitting at your desk at work, you're in the middle of writing a report, phone rings. That's an interrupt, right? Okay, got to stop what I'm doing, leave the mouse exactly where it is, and halfway through a sentence, deal with the phone. Oh, you've got to look up some information on the computer. Okay, Alt-Tab, go to your other application, find some stuff, hang up the phone. You've got to get back to where you were. So you've got to close down maybe the app that you ran, find where your mouse pointer is, and get back into that sentence. So you've got to pick up where everything left off. And that starts getting a little bit tricky, as we'll see. So the polling code, as I said, is fairly straightforward. You can get a bit tricky in terms of how you do that, in that you can actually write algorithms that could poll things a little differently. They don't have to do it necessarily polling things in order at particular times. Maybe you could poll something twice as fast as something else. Okay? But it's generally fairly easy to do. So the processor would look at the control registers to check the peripheral. If it's ready, you service it, then you check the next one, service it, etc. Okay, as I said, it's really ultra reliable because you have total control over what you're doing. Okay, and the coder can decide not to poll things if they want. Okay, so for instance, let's look at sending some data over a serial interface. Okay, so how would you do it? I've been talking pins and stuff now, but let's get back to, say, you want to send some real 8-bit byte out somewhere. Let's look at the Atmel AVR configuration. We have to pick something, right, if we're going to do an example. So I'm going to have to pick some architecture. I can't just leave it too generic. And if you want to send a byte over a serial port, you can write 2 lines of code to do it. That's nice, right? We don't have to worry about getting into nitty-gritty of setting registers, polling pins, all that sort of stuff. You just write 2 lines. And what do these 2 lines do? Well, first up, I'll say that these 2 capital letter things, I'll say things because we'll see later what they are, these are variables, okay, and they're defined in a header. Now, the header will be specific to the architecture that you're designing for, okay? So it might be slightly different for slightly different architectures, but the idea is that these things, the names would be universal in the family of chips. Okay, what they are they're memory mapped registers in the UART, in the Universal Synchronous Receiver Transmitter. So they're just spots for things to go or things to come in. And this little loop here basically will get that memory mapped register and apply via logical AND a mask to it. So what's not said here is this is called a mask. And it's an 8-bit number. It's 2 hexadecimal digits. And what it's doing is it's basically, if you do it in binary, right, it is masking off this bit here, 0, 1, 2, 3, 4, 5, or if you want 1, 2, 3, 4, 5, 6. If you want to go from 0 to 7 or 1 to 8. So it's the 6th bit that it's looking at in here. To turn that into a scalar, just a 1 or a 0. And as long as what's in here is, we've got to be careful, got inversion going on. As long as what's in here is 0, then this thing will keep running. So in other words, this little loop here basically just iterates, doing nothing pretty much, until this particular variable, or this masking of this variable here, becomes a 1. Okay? That actually indicates that the UART's ready. Then you invert it, then the while breaks. Down here, what's happening is that, remember how assignments work, obviously. If you're getting a bit confused, thinking this is a constant, that's a variable, how can that be around that way? Right, remember, we're assigning right to left. So X is actually sent to whatever that thing is. Okay, and so X is the thing of interest that you want to transmit. Okay, so let's have a look in a bit more detail about how would you send, say, a sequence of bytes. So that's sending 1 byte. You mask some register somewhere and then you assign what you want to send to some magic value. You can iterate over loops, no problems, but this is where things get a little bit messy. Not messy, inefficient, I should say. So let's say you want to now send 8 bytes, okay, sequence of bytes. So you're going to have a little loop here that's going to iterate between 0 and 7. When it hits 8, it'll stop, right? And what you're going to do is you are going to do the same little loop, but you're just going to loop it 8 times over, right, your variable here, which now holds the stuff you want to transmit. Okay, so wait until the UART is ready to send by checking that particular bit in that register here, and then basically pump out the data. So how long would this take to execute? So let's assume it's RS-232. So it has, which has a maximum baud rate of 57,600. Now, for our purposes, what's baud rate? If you've ever heard baud rate before, baud is a information theory quantity. Luckily, if you're just sending 1s and 0s, it's the same as bit rate. Okay, so we can think about that as bit rate. It gets more confusing when we send different symbols, multiple symbols. So for 1s and 0s, it's just bit rate. So that's our bit rate. If we are sending 8 bits, then, right, we can work out basically how long it takes to send the 8 bits. Now note that this is going to be a really rough estimate because RS-232 actually has start and stop bits as well, so it's really more like 10 bits. But let's just say we're sending a byte. And if the processor typically runs at a super fast rate, but the serial port's fairly slow, we can do the math, right? So you've got 139 microseconds. What's that, 10 to the 6? And you've got a clock rate of 18 megahertz, which is something like, what have I written down here? It's about 55 nanoseconds. So it comes out as something like, let's keep it simple. And this is one of the big problems of slow serial ports, that to send that sequence of bytes there, it takes 2,500 cycles. In other words, you're not doing much. That's a lot of processing power, reasonable little embedded speed of 18 megahertz, 2,500 cycles, because you are essentially waiting for the UART to stack everything up, right, and then clock it all out, and then you're stacking it up again, or loading in parallel and then clocking it out. Okay, so it's quite wasteful, perhaps, to do that. So we'll see via interrupts how we can actually probably improve this a bit better. Now, if you want to receive something via UART, it's very simple again. It makes programmers' life really easy. We can write a very simple while loop, where the only difference now is we're checking the same register, right, the serial register here, but we are masking it now with a different value. And what that does is that actually pulls off a bit that tests whether or not it's ready. So all of this ensures that the UART is full of data. Okay, remember, serial to parallel is what's happening, so you have to wait till it clocks in, and you've got to let the hardware tell you when it's done that. Okay, but there's a problem with this little piece of code here, in that what if the UART never receives anything? Right? Why would it never receive anything? What if someone pulls a wire off? What if there's a dodgy connection, right? Then this loop will never ever exit, right? Because the UART never receives anything. Because the only way this can exit is this little, the bit masking here would break the while loop. Right, so that's a difficult problem, right? Programmers may have to think about hardware faults here. And we'll talk about this later on in the course when we start looking at predictability of systems. All right, so the way to do things is to, instead of perhaps writing little loops like that where you're wasting thousands of cycles doing nothing, right, is to use interrupts to manage this. So instead of, this is polling, right? I should say, sorry, this is essentially polling. You are reading that register. The while loop is essentially whenever it's looping, is reading that register, it's polling the thing. Let's set up via interrupts now. Interrupts are fantastic, but they're also very dangerous, particularly for embedded systems. It's a very simple process. Processor set up code, good. Register something called an interrupt service routine. Bang, an interrupt happens, so a button's pushed, a packet of data has come into the UART. You then go and execute whatever you need to. While you're actually doing a task, if the interrupt happens, you switch context and you go and do the interrupt service routine. My little example is the phone call, right? Phone call comes in, oh, crap, got to put everything down and go across and do that, handle that. And eventually, when the phone call's finished, you go back to what you're doing, your normal task. Okay. So, interrupts have three things to think about. What's going to be the trigger, what the response is, and then how you actually design the thing that handles the interrupt services that we say. If you're interested, here is the code that lives inside an ATmega 168. When you actually program this thing, these are the first memory addresses inside the flash memory. There's instructions, they're all jump instructions loaded as the first few addresses in the memory space, interestingly. And the first instruction is actually a jump instruction to some other address. That's reset is some other vector where the actual code lives for the micro. And these are interrupt handlers, basically. So what happens is a trigger happens, say on an input pin, and the hardware is configured to modify the program counter, depending on what the interrupt is, to make it go to one of these addresses here. Yeah, these are all interrupts. Oh, yeah, most of these are interrupts. To go to one of those things. It will go to that address. Now, what's in that address is normally a fixed jump instruction, but an address that is chosen by you, okay, or by the compiler, right? And this will then, so hardware goes to here, looks here, grabs the jump instruction, finds the address of a little routine to run, and will then go to it. Okay, so it's hardware that's going to these known locations and finding the address of where to go to run things. So that's the trigger, and then the the response of the processor, the first thing it normally does is disables interrupts. Having an interrupt trigger repeatedly is a bad thing, as we'll see. So disable the interrupts, save what you're doing. In this case, push the program counter onto the stack, so where you were, like, my computer, where everything was, the state of everything, and then go and execute the instruction that's designated by this memory address here. Right, design of the interrupt service routine that actually then goes and sees what's happened and maybe might then pull some data out. You need to save and restore any registers it uses, re-enable interrupts before returning from interrupt. So I'll give you a quick quote, and I'll show you a nice little simulator to show you what's happening inside the CPU. So this is back in 1972. Dijkstra, who's done a lot of work in this area, says, in one or two respects, modern machinery is basically more difficult to handle than the old machinery. Firstly, we've got interrupts, occurring in unpredictable and irreproducible moments compared with the old sequential machine that pretended to be fully deterministic automation. Okay, so in the old days of computing, everything was fully deterministic, right? You could pretty much tell exactly what's going on step by step. But once interrupts came along, it allowed us to become more efficient, but it became the predictability of things almost go out the window, right? Because, as we'll see, interrupts can get quite messy. Just as an example, for those of you who are interested, there's a really nice, if I scroll all the way up, a little processor simulator. The address says WebSim. And what you can do is you can run, there are a few examples of different coding things you can run, and you can see what happens inside the control unit, inside the processor, and inside the memory. So for instance, I've just loaded a little bit of code up, and you can step through instructions. I won't talk too much about it, but you can see the assembly. There's very simple assembler instructions, adding and loading stuff, and that's the microcode that comes out of compiling all of that. Look at that, wow. And you can simulate it. So you can run the simulator and see, it's a very short program. But basically, so even this little program has loaded some registers with some values to do some processing. The program counter is pointing to the memory where it's operating at, the instruction registers holding the instruction, etc. You can see in this case, what does this have, 32 registers? Yeah, 32 registers. If an interrupt comes, you need to preserve exactly what's going on here. So in other words, typically you may have to save all of these values because you can't change them, right? It's just like, my phone call comes in, I can't turn back and suddenly there's a sentence missing from what I was writing, right? That makes no sense. So everything's stored, and that typically is program counter, all the register file, maybe some other things as well. But anyway, have a play. There's some really good examples. There's even one with interrupts in here as well, which you might want to just get a feel for things, and it'll show you the control words and stuff that are loaded. It's really good to play around with. So timed interrupts are, so we can handle I/O via interrupts, so when something arrives or when someone pushes a button, but timer interrupts are also hugely useful. And it kind of works the same way, just that there's an underlying timer that's ticking along, and that generates the interrupts. It's like an internal thing almost, okay? So the process is exactly the same. We set up a timer. The timer in the hardware ticks along. When the timer expires, it then jumps to an ISR in order to maybe service it or whatever. Yeah.
With this time interrupt, we expand
Yeah. So we've got to be careful about what tasks and stuff are. So the current instruction that it's executing, right, would be, once it's finished, it would then go off to the interrupt service routine. Okay, so in essence, if you're doing a big calculation or something, right in the middle of it, bang, you're off to go and service that interrupt. Yep, so you're suspending what you're doing. Okay, so I'm going to run through a quick example of how to set up the interrupt and why it's quite easy from the developer's perspective, but to find out what's really happening, you have to start digging. So I don't want you to get too hung up over this example, but this is using an 18 mega AVR, which has a frequency of 18.4 megahertz. Now, if you wanted to set up a little timer, and the timer would generate an interrupt every millisecond, you need to set up a whole bunch of registers here. Okay, these are specific to the architecture. Now, what do these things mean? There's timer control registers. There's two segments to that, 16 bits. Okay, so there's a low end and a high end to it, A and B. There's a timer interrupt mask here, which basically enables things to happen. And then there's an output compare register here. So how do you generate timed events? Well, it's easy. You basically just preload a value in a timer. Just think of a big counter. Let it tick down, and when it hits 0, it generates an interrupt. The only tricky thing is basically to work out the correlation between what you need to set the timer value as, the output compare register, to your system clock and to what's called a prescale value. Okay, so you can read a little bit about it here, but basically you have options. If you've got a certain system clock, you can divide it by a certain number and then choose how many of those ticks to count. And so here, the value that you're going to set for the timer is the system clock divided by the prescale value times the interrupt frequency minus 1. It's kind of messy to do this calculation. It's really annoying always to have to do this. But as I said, it depends on how you scale down that clock. That's just a big ugly clock divider that's enabled with a particular value here that's selectable. Now that's chosen by setting the option in the timer mask register. Okay, so what actually happens? So if you want to write the code, this would be the code that you would write, right? For that example there. You'd set those 2 registers, 3 registers, 4 registers, and that automatically sets up the hardware to trigger an interrupt every 1 millisecond. Now, if you look at that code, it looks, it's just setting things to be equal to stuff. How is that actually writing to registers, timer control registers, output compare registers, all of that sort of stuff in the hardware? How the heck is that happening? Turns out these are magic things that are defined for a particular architecture, AVR, in the I/O header file. Okay, now if you go digging, you're going to find a whole bunch of stuff to look for, and all that stuff we'll cover next lecture, but they are the locations of the things you need to find. And when you pull them out, this weird pointer-ish stuff comes out to a memory location, setting it equal to 0. What on earth is this? All right, we'll look at this next lecture, and then we'll talk a little bit about the hazards of interrupts. In the meantime, have a play with that little simulator. It's really fun to muck around with and see how things work.